Okay, so now remember, we were assuming our numbers, 3, 15, 85, 493, and 28, 71, and even the first one was 1, were somehow powers of lambda. And we found 3 choices for lambda. Okay? Our cat wants to go outside. So we can call this the 0 term,
Yep.
the 1 term, the 2 term, the 3 term. So we should have 1 equals maybe some power, this to the 0 power, plus this to the 0 power, plus this to the 0 power. Some combination of those.
Alright.
So I will call those x times 1 to the 0 plus y times this to the 0 plus z times 3 minus 2 root 2 to the 0.
Okay, that makes sense.
3 equals x times 1 to the 1 plus y times 3 plus 2 root 2 to the 1 plus z times 3 minus 2 root 2 to the 1. And then 15 equals x times 1 squared plus y times 3 plus 2 root 2 squared plus z times 3 minus 2 root 2.
And the x, y's, and z's all stay constant.
Yeah, so it's some linear combination of powers of 1, powers of 3 plus 2 root 2, and powers of 3 minus 2 root 2.
Alright.
Okay? And then if we solve this, which is a 3 by 3 system, so that's what you're studying in linear algebra right now. If we solve this system, we hope that when we put in the third power, we get 85. Once we know what x, y, and z are, and when we put in the fourth power, we get 493. When we put in the fifth power, we get 2871. And then we'll be able to find all the numbers after that. Now, so does it surprise you that combinations of 1, 3 plus 2 root 2, and 3 minus 2 root 2 are always integers?
No, you have a plus and a minus here, so you'd think that these might cancel each other out.
Okay, good. Good observation.
So that might mean that you might want your y and z coefficients to be the same? Possibly?
Maybe they'll be the same. How do I solve a system like this?
You could use a matrix and solve it that way.
How? Tell me.
You're gonna have a matrix, like a 3 by 3 matrix. I think it's gonna be these terms multiplied by x, y, z.
Yeah.
Equals this.
Yeah.
And then we're gonna row reduce it, get it down to some pivots, and maybe it'll work with that with non-integers. Maybe it won't. It should work.
You're concerned that because these aren't integers it won't work?
It might not simplify as nicely.
Yeah. Okay. Right. The calculations are going to be messy. They're going to be messy. So actually, what I'm going to do is do them on a computer. We'll have Mathematica solve this for us. But this is a nice 3 by 3 system, and then we're gonna find a really nice surprise that the nth number is going to be whatever we find x to be times 1 to the n plus y times 3 plus 2 root 2 to the n plus z times 3 minus 2 root 2 to the n, and we're going to find all these integers.
All right.
That's a pretty cool application of solving. There was one other thing I was going to say. Oh yeah. What can you tell me about the number 3 minus 2 root 2?
It's pretty small.
Okay, it's approximately what?
Well, root 2 is about 1.4, so 2 root 2 is about 2.8, so 3 minus 2 root 2 is like 0.2.
Okay, good. So what about 3 plus 2 root 2?
So that's going to be like 5.8,
okay.
Almost 6.
And what can you tell me about powers of 1?
Those are always going to be 1.
Okay, so as n gets large, what are we going to start looking more and more like here?
So it's going to look more and more like this to large powers, so large powers of around 6.
Yeah. All right, cool. So we'll go to Mathematica now.